In the summer of 1940, the United States Army was a shadow of the force it would become. Ranked 19th in the world, its military power was negligible, a sleeping giant yet to be roused. As German panzer divisions swept across Europe, their blitzkrieg tactics rewriting the rules of modern warfare with over 3,000 tanks, America could muster exactly 66 medium tanks in its entire arsenal. The mathematics was terrifying. At the Rock Island Arsenal, the nation's primary facility for armored vehicle construction, the production method was more akin to sculpture than manufacturing. Each tank was a custom creation, its components hand-fitted by skilled craftsmen in a process that was painstaking, meticulous, and agonizingly slow. At a rate of perhaps 3 medium tanks per month, fulfilling an order for 1,000 vehicles, the bare minimum required for a credible defense would take an astonishing 277 years. This was the grim reality that confronted Lieutenant General William Knudsen, the man President Franklin Roosevelt had charged with mobilizing American industry for war. Knudsen, a former Ford executive who understood the power of mass production, knew the government arsenals could never meet the coming demand. He needed a new approach, a new partner, a new philosophy. On a June day in 1940, he picked up the phone and made a call that would alter the course of war. On the other end of the line was K.T. Keller, the formidable chief executive of the Chrysler Corporation. Knudsen's question was direct. Could Chrysler build tanks? Keller's response was brutally honest. "I don't know," he said. "I've never seen one of these things." Keller, accompanied by his chief engineer, B. Hutchinson, traveled to the Rock Island Arsenal to see for himself. What they witnessed confirmed their worst fears. It was, in Keller's words, not manufacturing, it was sculpture. Skilled artisans moved around a stationary 19-ton vehicle, slowly fitting and adjusting each of its 8,000 components. An astonishing 60% of all production time was consumed by this custom fitting. Keller recognized instantly that this craft-based system was a dead end. It could not be scaled, new workers couldn't be trained fast enough, and it could never produce 1,000 tanks in 18 months. Back in Detroit, Keller convened his tank committee, a brain trust of Chrysler's finest engineers, including Hutchinson and the chief production engineer, Owen Skelton. Skelton framed the problem in terms they understood. An automobile is 2,000 pounds of steel, rubber, and glass assembled from 5,000 parts. We make 3,000 of them per day. A tank is 30,000 pounds of steel assembled from 8,000 parts. The only difference is what we're assembling. It was a profound insight that cut through the mystique of military hardware. A tank, however complex, was just another mechanical assembly. From this core belief came the revolutionary Chrysler method. B. Hutchinson proposed its foundational principle. Every single component would be manufactured to precise automobile tolerances. If every part were made to an exact standard, they would fit together perfectly every time, without the need for custom adjustment. This would eliminate the craftsman from the equation and turn assembly into a predictable, repeatable process. Keller presented this radical vision to the Army Ordnance Department. His argument was irrefutable. We don't build tanks the Army's way. We build them our way. You need 1,000 tanks in 18 months? We can deliver them. Can anyone else? The Army, faced with an impossible demand, reluctantly agreed. In August 1940, Chrysler was awarded the contract to build and operate the first factory in American history dedicated to the mass production of tanks. A 113-acre tract of farmland in Warren Township, Michigan, was selected. The legendary industrial architect Albert Kahn was commissioned to design a facility of unprecedented scale. A main building covering 1.25 million square feet, with bomb-resistant 3-foot-thick concrete walls. Ground was broken on September 9, 1940. The Detroit Tank Arsenal was about to be born. built on a philosophy that would transform American industrial might into a war-winning weapon. Yet even as the foundations were being laid, no one could foresee the full extent of the production crisis that loomed, or the role another automotive genius would play in unleashing its ultimate potential. By August 14, 1942, 2 years after Chrysler had accepted the challenge, the Detroit tank arsenal was a functioning, if deeply troubled, reality. Plant manager John Cadden stood on the cavernous factory floor, a stopwatch in his hand, his gaze fixed on the assembly of hull number 217. The factory itself was an industrial marvel, but the process taking place within it was a frustrating hybrid, a compromise between Chrysler's automotive vision and the Army Ordnance Corps' rigid traditionalism. The workers, trained by Army specialists, moved with methodical precision. Every movement followed the official technical manual. Every weld met inspection standards, and every bolt was torqued to specification. The problem was not the quality of the work, it was the crippling passage of time. Hull 217, an M4 Sherman medium tank, had been sitting on the assembly floor for 11 days. According to the production schedule dictated by Army procedure, it would require another 8 days before it was complete. 19 days in total. 19 days to produce a single, solitary tank. At this rate, the Detroit Tank Arsenal, the largest and most advanced tank factory in the world, would produce approximately 420 tanks in a year. The numbers were a death sentence. The United States Army had requisitioned 10,000 tanks for the year 1943 alone. At its current pace, the arsenal would need 24 years to fulfill a single year's order. The mathematics of defeat were being written in man-hours and assembly time, a slow-motion catastrophe unfolding largely unnoticed by the very management overseeing it. The M4 Sherman itself had been designed for production efficiency. Conceived in a remarkable 78-day sprint between April and June of 1941, it prioritized practicality over technical sophistication. Its Wright R975 radial engine was already in mass production for aircraft. Its 75mm main gun used existing ammunition. Its suspension adapted proven components, and its hull was designed for welded construction to minimize complex casting. And yet, even with this production-friendly design, manufacturing remained agonizingly slow. The Lima Locomotive Works in Ohio, which received the first contract in August 1941, took 6 months to deliver its first tank. By April 1942, it had accelerated to a rate of 1 tank per week, still impossibly inadequate. The Detroit Tank Arsenal was supposed to be different. It represented America's commitment to winning the war through industrial might. But the Army Ordnance Corps technical advisors, steeped in tradition, insisted that tanks were fundamentally different from automobiles. The complex armor, the specialized weapon systems, the sheer weight of the components, all, they argued, demanded the traditional stationary assembly methods used to build custom locomotives. The first Sherman rolled off Detroit's floor on April 11, 1942. That month, total production was 12 tanks. May saw 37. June hit 61. It was progress, but it was a drop in the ocean compared to the thousands of tanks Allied strategy demanded every month. The problem wasn't worker skill, material supply, or equipment. The problem was the methodology itself. Each hull sat stationary as teams of workers swarmed around it, installing components in a rigid sequence. The process was plagued by constant bottlenecks. Workers waited for specialized tools. They waited for inspection approvals. They waited for the previous operation to be completed. It was craftsman production applied to the brutal calculus of industrial warfare, and it was impossibly slow. But on that August day, someone else was watching Hull 217. Standing off to the side, A 47-year-old civilian production consultant named Charles Sorensen was scribbling calculations on the back of a requisition form. Sorensen, who had spent 36 years at Ford Motor Company as Henry Ford's right-hand man, was the architect of the moving assembly line, the man who had reduced the production time of a Model T from 12 hours to 93 minutes. Now a $1-a-year consultant for the War Production Board, he was conducting an unauthorized time-motion study of tank construction. What he saw violated every principle of efficient manufacturing he had spent his career perfecting. Tanks were being built like bespoke machinery. Workers moved around a stationary product instead of the product moving past stationary workers. The difference seemed subtle, but its implications for efficiency were profound. Sorensen's calculations were as shocking as they were audacious. He believed that by applying the principles of proper flow manufacturing, the production time for a single M4 Sherman tank could be slashed from 19 days down to just 48 hours. His colleagues at Chrysler thought he was insane. The Army ordnance officials declared it impossible. Tank construction, they insisted, was not automobile assembly. The complexity, the precision, the weight, all demanded the methodical, stationary approach. Charles Sorensen, the man who had put America on wheels, was about to prove them all wrong. He was about to perform an impossible trick that would transform American armored vehicle manufacturing from an artisanal craft into an industrial avalanche, burying the German Wehrmacht under a relentless tide of American steel. Sorensen had retired from Ford in 1941, but retirement during wartime felt like desertion to a man who had built his life on the promise of American industry. When the War Production Board asked him to consult on tank manufacturing, he accepted immediately. His first 2 weeks at the Detroit Tank Arsenal were spent in meticulous observation. He photographed operations, interviewed workers, and calculated theoretical production rates, reverse engineering the entire assembly process. His analysis identified 173 discrete operations required to assemble a Sherman tank. Under the current system, these operations took a total of 456 hours of labor, spread out over 19 agonizingly long days. Sorensen's revolutionary insight was recognizing that the work itself didn't actually require 19 days. The process required 19 days because of the waiting. Time spent waiting for the previous operation to complete. Time waiting for tools and components to be delivered from distant storage cribs. Time waiting for an inspector to sign off on a weld. Time waiting for a specialized crew to become available. The entire factory was a monument to wasted time, a system where the most common activity was inaction. His solution was as simple in concept as it was radical in application: continuous flow manufacturing. Instead of workers moving to stationary tanks, the tanks themselves would move past a series of specialized workstations. Each station would be a self-contained universe, equipped with all the necessary tools, components, and personnel for a single, specific task. Workers would perform the same limited set of operations over and over, developing extraordinary speed and proficiency. Inspection would be continuous, integrated into the line itself rather than acting as a roadblock. The goal was to eliminate waiting entirely, to create a system where every moment was productive. In August 1942, Sorensen presented his proposal to a deeply skeptical audience of Chrysler management and Army ordnance representatives. The reaction was immediate, bordering on outright hostility. Brigadier General James Wesson the chief of Army Ordnance, stated flatly that tanks were not automobiles and could not be built like them. The precision, the complexity, and the sheer mass of the components, he argued, made a moving assembly line a dangerous fantasy. Chrysler's own engineering staff, wary of disrupting their existing system, sided with the Army. They documented a litany of technical obstacles they deemed insurmountable. A tank hull weighed 15 tons, far too heavy for any standard conveyor system. Turret installation required massive overhead cranes that could not operate effectively over a moving line. Final drivetrain assembly involved components weighing over a ton each. The critical process of hull welding required the vehicle to be held in a stationary position to ensure proper penetration and cooling. Sorensen, unflappable, countered every objection with a specific, practical solution. For the 15-ton hulls, he proposed using heavy-duty conveyors designed for locomotive shops. For turret installation, he suggested mobile gantry cranes that could move in sync with the assembly line. Heavy components could be pre-positioned at specific stations using dedicated lifting equipment. Hull welding could be completed in dedicated stations where the hull would pause for a precisely timed interval before continuing its journey down the line. The debate raged through August and September. Army Ordnance remained adamantly opposed, citing regulations that required specific inspection protocols incompatible with a moving target. Chrysler management worried about the massive cost of reorganization and the inevitable production disruption during the transition. Finally, with the project on the brink of rejection, Sorensen played his trump card. He proposed a wager, a live demonstration. He asked for one corner of the factory and the resources to build a small prototype assembly line. On that line, his team would attempt to build 3 tanks using his continuous flow methods. Meanwhile, the main factory floor would continue with traditional assembly. If his approach could produce 3 complete tanks in less time than the traditional method produced 1, Chrysler and the Army would have to authorize a full-scale implementation. It was a high-stakes gamble, and the future of American tank production hung in the balance. The demonstration began on October 1, 1942. Sorensen's team was given a space in Section D of the factory, an area previously used for subassembly work. They had 3 weeks to design, build, and operationalize a prototype line from scratch. The challenge was enormous. They needed custom-built conveyors capable of bearing 15-ton loads, specialized tooling positioned for continuous access, and material handling systems for components weighing up to 2,000 pounds. Most critically, they needed to create a synchronized workflow where every station's output perfectly matched every other station's capacity. Sorensen brought in specialists from Ford's legendary River Rouge plant, the most advanced manufacturing facility in the world. They designed hydraulic lift systems for heavy components, custom roller conveyors with reinforced load bearings, overhead delivery systems for small parts, and automated welding fixtures to hold the massive hulls in perfect position. The prototype line was 180 feet long and consisted of 11 primary workstations. Each station was meticulously designed for a specific set of operations, timed to be completed in exactly 12 minutes. Station 1 received raw hull components. Station 2 performed primary hull welding. Subsequent stations installed internal structures, suspension, transmission, the engine, electrical systems, and finally the completed turret, which was built on a parallel assembly line. The final stations handled external components, systems integration, fluid fills, and operational testing. On October 23rd, the first trial run began. The result was a catastrophe. The custom conveyors jammed under the immense weight of the hulls. Welding fixtures failed to position components correctly. Workers trained in general assembly couldn't adapt to the repetitive station-specific tasks. The timing was a disaster, with different stations completing their work at vastly different rates, creating chaos and gridlock. Army ordnance observers watched the shambles and declared the experiment an abject failure. They demanded Sorensen abandon the project immediately. Chrysler management, concerned about the wasted resources, agreed. Sorensen refused to quit. He had seen these same problems during the initial rollout of the Model T assembly line in 1913. Early failures didn't prove a concept was impossible. They revealed specific problems that required specific solutions. He requested 2 more weeks. For the next 14 days, the team worked in a frenzy of furious improvisation. Engineers redesigned the conveyor supports, reinforcing them for better load distribution. Welding fixtures were modified on the spot, based on the actual geometry of the hulls rather than the blueprints. Workers received intensive, hands-on retraining, focusing only on the specific tasks required at their assigned station. Operations were split or combined to rebalance the cycle times. The second trial run began on November 9th. The improvement was dramatic, but the line was still imperfect. Tanks moved, but with frequent stops and starts, as the team solved problems on the fly. They managed to produce 3 tanks in 8 days, better than the traditional method, but a far cry from Sorensen's promised 2-day timeline. The final breakthrough came on November 16th, when Sorensen implemented his most radical innovation, the moving crew concept. Instead of having workers remain at fixed stations as the tank passed by, he assigned small, specialized crews to a single hull. These crews would move with the tank down the line, performing their specific operations, be it electrical wiring or drivetrain installation, while the vehicle was in continuous slow motion. This elegant solution eliminated the jarring station-to-station transfer delays and maintained a constant, fluid momentum. The third and final trial run began on November 23rd, the week of Thanksgiving. Sorensen had bet his entire reputation on this attempt. Failure meant the end of the experiment and his likely banishment from the war production effort. The results were beyond even his own optimistic projections. 3 complete Sherman tanks, fully assembled, tested, and ready for combat, emerged from the prototype line in just 41 hours. That was less than 14 hours per tank compared to the 456 hours required by traditional methods. It was a staggering 96.3% reduction in assembly time. More impressively, quality had not been sacrificed for speed. Army inspections revealed no significant defects. The armor welds passed ultrasonic inspection. Test drives showed all systems functioning perfectly. The tanks were combat ready. The Army ordnance officials who had been his most vocal critics were stunned into silence. Brigadier General Wesson, the man who had personally declared continuous flow assembly impossible, inspected all 3 tanks himself. He found no evidence of rushed construction or compromised quality.
Convinced, he gave the order for the immediate and full-scale implementation of the system across the entire Detroit tank arsenal. The transition began on December 1, 1942. The challenge was staggering: to completely reorganize a factory floor covering 1.6 million square feet, dismantle traditional workstations, install miles of new assembly lines, retrain thousands of workers, and redesign the entire supply system, all while maintaining minimum production to meet the urgent demands of the war. Sorensen divided the factory into 4 massive parallel assembly lines, each capable of independent operation. This redundancy was crucial. It meant a mechanical problem on one line wouldn't halt the entire factory, and it allowed for a phased transition. Line A began continuous flow operation on January 7, 1943. Initial output was cautious, 1 tank every 8 hours. But as workers gained experience and engineers refined the process, the cycle time decreased with astonishing speed. By the end of January, Line A was producing a tank every 4 hours. Line B converted on February 15th, Line C on March 1st, and the final line, Line D, on March 22nd. By April 1, 1943, less than 4 months after the transition began, all 4 lines were operating simultaneously. The arsenal was now producing 24 tanks every single day, an 8-fold increase in output.
But Sorensen wasn't satisfied. His original calculations indicated a 1-hour cycle time was achievable. He relentlessly attacked the remaining bottlenecks. Turret installation, a delicate operation requiring precision positioning, was slowing the line. His team designed a specialized turret mating station where hulls would pause for just 6 minutes while mechanically assisted arms lowered the turrets into place with microscopic precision, eliminating a 30-minute delay. The 1,150-pound Wright radial engine presented a similar challenge. Sorensen's team developed an automated engine dolly that carried the engine alongside the moving hull, allowing installation crews to work while the tank continued its journey. For mounting the heavy transmission and differential units, they created mobile, floor-mounted lifts that tracked with the hulls down the line, replacing the inefficient overhead cranes. These refinements were implemented throughout April and May. By June 1st, the cycle time had dropped to 90 minutes per tank. By June 30th, it was 75 minutes. On July 31, 1943, the Detroit tank arsenal achieved a cycle time of 63 minutes, slightly faster than 1 complete M4 Sherman tank every single hour. The transformation was complete. The same factory that had produced a mere 12 tanks in April 1942, now, using continuous flow assembly, produced 721 tanks in July 1943. It was a 60-fold increase in just 14 months. The statistical comparison was breathtaking. Traditional assembly required 456 man-hours per tank. Continuous flow required just 48. Labor efficiency increased by 950%. Factory space utilization improved by 400%. And astonishingly, despite the incredible speed, quality defect rates plummeted by 73%, as specialized workers developed an unparalleled proficiency at their single, repeated tasks. The arsenal of democracy had been truly unleashed. Sorensen's methods were a revolution that could not be contained within the walls of a single factory. The success at Detroit became the new blueprint for American industry. The Fisher body tank arsenal in Grand Blanc, Michigan, converted to continuous flow in April 1943.
The Pacific Car and Foundry Company in Washington followed in May. The Federal Machine and Welder Company in Ohio began its conversion in June. By the end of 1943, American factories were producing 2,100 Sherman tanks every month, a more than tenfold increase from the 200 per month being built in mid-1942. This surge was not the result of building more factories. It was the result of a revolution in manufacturing philosophy.
The strategic impact of this production avalanche was devastating to the Axis powers. German intelligence, basing its estimates on traditional manufacturing rates, believed American tank production capacity was approximately 300 units per month. When the true figures, exceeding 2,000 per month, became undeniable, German planning assumptions collapsed. General Heinz Guderian, Inspector General of German Armored Troops, wrote in his diary in November 1943, "Intelligence reports indicate American tank production has increased tenfold within 1 year. If accurate, this represents industrial capacity beyond our ability to counter. We cannot destroy tanks faster than they manufacture them." In December 1943, Albert Speer, the German armaments minister, presented Hitler with the grim comparative figures. At its absolute peak, German industry could produce 540 tanks per month. America alone was producing 2,100. This 4-to-1 advantage in production made a German victory in any extended conflict a mathematical impossibility. The Sherman tank, often criticized for being technically inferior to the heavier German Tiger and Panther tanks, would win the war through overwhelming numerical superiority, a superiority enabled by Sorensen's production methods. The Normandy invasion demonstrated this advantage decisively. Between June and August of 1944, American forces landed 2,100 Sherman tanks in France. Though German forces destroyed approximately 800 of them in combat, replacement tanks arrived from the factories faster than the losses could accumulate. By September, American armored strength in France actually exceeded its D-Day levels. In stark contrast, German panzer divisions withered on the vine. The elite 2nd SS Panzer Division, Das Reich, landed in Normandy with 89 tanks. Over the next 3 months of brutal combat, it received 0 replacements. By September, the division was shattered, operating with just 14 functioning tanks. This production miracle extended beyond the tanks themselves. With the output of standard M4 Shermans secured, the same chassis could be used for numerous variants without compromising the main battle tank supply. The M7 Priest self-propelled artillery, the M10 tank destroyer, and the M32 tank recovery vehicle all used Sherman components. This parts commonality, itself a result of the mass production approach, simplified logistics and maintenance on an enormous scale. Sorensen's revolution had not just built tanks, it had created an entire self-sustaining armored ecosystem. It was a system that could absorb punishing losses and still press the attack, an industrial leviathan that the finest German engineering and battlefield tactics could not hope to defeat. The principles Sorensen championed at the Detroit Tank Arsenal radiated outward, transforming the entirety of American war production. The Army Ordnance Corps, initially hostile to his civilian expertise, eventually embraced continuous flow manufacturing across all weapons production. Artillery shell production, implementing assembly line methods, surged from 2 million shells per month in early 1942 to 18 million by mid-1943. At the Lake City Army Ammunition Plant, continuous flow loading lines churned out 4 million rounds of small arms ammunition every single day. Sorensen had proven a fundamental principle.
Complexity does not preclude efficiency. It simply requires a different, more intelligent organization of work. This transformation was powered by an equally significant human revolution. At its peak, the Detroit tank arsenal employed 40,000 workers. Under traditional methods, this workforce might have produced 800 tanks a year. Under Sorensen's system, they produced over 8,000, a tenfold increase in labor productivity. This was not achieved by forcing people to work harder. In fact, workers on the continuous flow lines reported less physical strain than in traditional assembly. The system eliminated wasted effort, time spent searching for tools, carrying heavy parts, or waiting for the previous crew. Specialized stations meant every movement was productive and ergonomic. The psychological reward was also immense. Watching completed tanks roll off the line every hour instead of every few weeks provided a tangible connection to the war effort that boosted morale and satisfaction.
The legacy of this industrial revolution extends into the modern era. The core principles, breaking complex assemblies into simple, repeatable operations, continuous flow to eliminate waste, specialized tooling, and synchronized timing became the foundation of modern manufacturing. The famed Toyota production system, developed in the 1950s, owes a direct debt to these wartime innovations. Its creator, Taiichi Ohno, meticulously studied Ford's production methods and specifically examined the manufacturing miracles of World War II. Concepts like lean manufacturing, just-in-time delivery, and the Kanban system all reflect the principles proven on the floor of the Detroit tank arsenal. The Sherman tank itself, a product of this rapid production system, proved remarkably durable and reliable, dispelling the myth that mass production inherently compromises quality. Shermans remained in frontline service with various armies for decades after the war, with some nations operating them into the 1990s. This longevity was a testament to the consistency of the assembly line, where tanks built to identical specifications with precisely calibrated tools showed remarkably uniform performance. The economic efficiency was just as critical. A Sherman tank cost approximately $50,000 in 1943. A German Panther cost nearly 3 times as much. This cost advantage, driven by manufacturing efficiency, allowed America to deploy armor lavishly, making the Sherman a ubiquitous presence on every front. The final tally tells the story. During World War II, the United States produced over 49,000 Sherman tanks. Germany, in the same period, produced fewer than 8,000 Panther and Tiger tanks combined. Combined with Soviet production of the T-34, the Allies achieved a crushing numerical superiority that stemmed not from a single superior design, but from a superior manufacturing philosophy. German tank production remained essentially artisanal. Their complex Tiger and Panther tanks required hand-fitting of components and extensive post-assembly modification. The quality was often superb, but the production rate was fatally slow, a result of a military doctrine that equated customization with quality. America, by contrast, embraced standardization, simplification, and systematization. It was a philosophical difference that determined the war's material balance. Charles Sorensen died in 1968, having lived to see his principles become the global standard. His 1956 autobiography devoted 3 chapters to his time in tank production, which he described as his most satisfying professional achievement. Building Model Ts taught me manufacturing principles. Building Sherman tanks proved those principles could win wars. His impossible trick was not magic.
It was the result of a relentless willingness to challenge assumptions, the expertise to recognize inefficiency, and the credibility to force change against powerful institutional resistance. It was the story of how an assembly line became as decisive as a battle line, proving that in a total war, an adequate weapon supplied in overwhelming quantity will always defeat a superior weapon supplied in insufficient numbers. The transformation from 19 days to 60 minutes was more than a manufacturing miracle. It was the blueprint for victory.